My name is Marcin Hoffmann, and I represent both Rimedo Labs and Poznan University of Technology. Today I will present my paper entitled Signaling Storm Detection in IIoT Network based on ORAN architecture. To begin with, the IoT devices are characterized by low hardware complexity, resulting in low computational power and low cost. These features make them relatively easy to be hacked and used to attack the network infrastructure. A possible attack scenario is a so-called signaling storm attack, where the adversary utilizes standard mechanisms of network control plane to cause denial of service. For example, flooding the network control plane with repeated registration requests. On the other hand, during registration, IIoT devices report to the G-Node B their timing advance, which is the time offset related to the signal propagation between the G-Node B and IIoT devices. Because IIoT devices are in most cases stationary, the timing advance is constant for them and proportional to the distance from G-Node B. It would be beneficial to identify adversary devices in the early stage of the registration process in the radio access network to protect the core network resources. This can be hard to achieve in state-of-the-art mobile networks, where both hardware and software are provided typically by a single vendor with only a limited possibility of affecting their configuration. In this paper, we propose a signaling storm detection xApp to detect abnormal activity of IIoT devices at the beginning of their registration procedure. The xApp is deployed within the ORAN architecture. The concept of ORAN enables interaction with RAN through the dedicated interfaces. For example, E2 interface can be used to intercept RAN protocol messages. In the figure we can see the message flow diagram between IIoT device, G-Node B and xApp. With the use of the ORAN interfaces, the random access response, which carries the timing advance of the IIoT device, can be copied to the xApp to perform statistical analysis in order to detect signaling storm. Later on, when IIoT devices sends the RRC setup request, it is also forwarded to the xApp. At this stage, based on the signaling storm detection result, the G-Node B is notified by xApp to either reject RRC setup request or accept it and proceed with IIoT device registration in the core network. The signaling storm detection is based on the so-called Key Performance Indicator profiles, namely KPI profiles. In our case, the KPI profile contains the long-term statistics of RRC setup requests associated with observed values of timing advance. It is mean number and standard deviation. In the figure we can see representative examples of such KPI profiles for several values of timing advance. During the network operation, the number of RRC setup requests is constantly monitored for each observed timing advance. To detect signaling storm, it is compared against the values from the KPI profile to compute the so-called anomaly value, as given in the equation on the right. If the anomaly value exceeds the gamma threshold, the xApp identifies signaling storm. We have verified the proposed algorithm in terms of computer simulations. The simulation parameters are depicted in the table. We have considered a single cell with 2 km radius that provides connectivity for 100 legitimate IIoT devices and 5 adversaries. The legitimate devices send their RRC setup requests with exponential distribution of mean rate parameter equal to 5 requests per hour. The rate parameter is changing over the daytime, resembling a sinusoidal function. The adversary performs signaling storm attack within the intervals following the exponential distribution with rate equal to 3 attacks per day. Each attack consists of 100 consecutive RRC setup requests sent within the interval of 5 seconds. We have compared the signaling storm attack detection for different thresholds of anomaly detection for 20-day-long simulations. The resultant probability of false alarm and signaling storm attack detection is depicted in the slide. It can be seen that for the low value of gamma, both the probability of detection and false alarm is very close to 1. the probability of false alarm can be decreased to 1.5% by setting gamma to 6.5. This comes at the cost of the probability of detection degradation to 92%. The proposed method allows to balance both probabilities by setting a proper gamma threshold, depending on the network operator's requirements. The following conclusions can be formulated. The utilization of Open RAN architecture enables the detection of signaling storm attack at an early stage of the adversary registration process. By properly setting the threshold parameter, the proposed signaling storm attack detection algorithm can offer high detection probability while causing only a few false alarms. Thank you for your attention.